Department of Computer Science and Engineering, University of Illinois, UIC, Chicago, US, renowned for his groundbreaking contributions in machine learning, and with a PhD in artificial intelligence from the University of Edinburgh. Sir's expertise spans sentiment analysis, lifelong learning, and natural language processing. His prolific research has earned him prestigious awards, including the ACM SIGKWD Innovation Award. His publications are listed in top-tier conferences and journals, along with his four authored books, underscore his profound impact on the field. With his wealth of experience and profound insight, he is poised to ignite our imaginations, challenge our perspectives, and spark meaningful conversations that will resonate long after this session concludes. So, without further ado, I invite you to sit back, engage your minds, and open your hearts as we welcome Dr. Bingu for his keynote speech on continual learning in the open world.
Thank you very much for the invitation, and it's a great pleasure to give this talk. And my talk is going to be about continual learning in the open world. So sometimes continual learning is also called lifelong learning. So in terms of traditional learning paradigm, and we normally do what is called isolate the single task learning, and we are giving a task and giving a data set, and then we get a learning algorithm, and then learning algorithm produce a model, and the model goes to application. So there are a number of key witnesses about this particular paradigm, although it has been really very successful. So one of those weaknesses is the closed world assumption, which basically means when you come to the application, there's nothing new and nothing novel will happen. So whatever you see in the testing or in the application environment, and you have already seen at training. So that's not the case in real life. In real life, we're talking about open world, which means there are lots of novelties and lots of unexpected things happening. And how do we detect and how do we learn continuously? And that's basically the objective of this this research and also this particular talk. So another, obviously, the weakness is no continual learning and no knowledge accumulation or transfer. And also, there's no learning after deployment. So when we have a model and then we go for application, and in the application, the model will be applied, will be used, but will never be changed. But that's not suitable for real life application. For example, you have a robot which goes to basically face the real world, that goes out and then doing things, and then obviously you will see lots of things probably you've seen before, and then how do you cope, how do you adapt, how do you detect, how do you learn, and to get yourself more smarter and smarter. So continual learning is defined in a fairly simple way, which basically means it learns a sequence of tasks incrementally, and each task is a training data set. We're talking about this supervised learning. Of course, it can be unsupervised learning as well. So we have data set for each task, and normally we do this in neural nets, but of course we can also use sort of support vector machines or other type of techniques. So what is a task? The task in the supervised sort of setting is essentially a set of classes to be learned. So as time goes by, we learn lots of classes, and a set of classes are sometimes we call it a task, because this set of classes may have some kind of relationship with each other, or maybe performing a specific task. So the goal is to learn each task incrementally and without forgetting, without catastrophic forgetting, which basically means when you learn a new task, and if you are using the same neural nets, and you have to change the parameters in the neural nets, and then which means you are destroying or somewhat disturbing or sort of updating the parameters of the previous tasks. And then in some sense, you are basically going to downgrade the performance of those previous tasks. And that's called catastrophic forgetting. And this is a very serious problem, and it's extremely difficult to deal with. The second issues, or the second sort of objectives or the goals we want to achieve is knowledge transfer. So after we learn a lot of tasks, and then when we learn the next task, n+1 task, and then we want to learn better. and then more efficiently, probably was less data and was more accurate result. So if we see this in the picture, it's something like this. We have a sequence of tasks T1, T2, and Tn and Tn plus 1, which is the new task. Sometimes we also call it the current task. Then as time goes by, we also have future task. So when we have this new task, and then we have the data, and then we have this continual learner, and then we also have knowledge base, which basically means we have learned something in the past, and those things stays in a network. And then when we learn this new task, we might be able to leverage some of this knowledge from the previous task, learn from previous task, and to make this particular task learn better, learn more efficiently and more accurately. And then we produce the model, and the model goes to application. Again, in this case, we have no change, no model change in the application process. So model stays the same. So the assumption, of course, in this case is the data and the task, the task and also the training data are given by the human engineers or human users. So the system does not take any initiative to basically collect data and to discover tasks. But when we come to the open world, and the system itself has to detect new tasks and also acquire ground truth training data, and which is basically continual learning in the open world. So in terms of continual learning, there are actually three popular settings. And the first one is called task incremental learning. So this setting is essentially is training a separate model for each task. So the models are separate, and every model has a task ID or some other kind of identifier which is provided at test time. So basically means at the test time, I tell you which task I'm using, and then you can use that specific model for that particular task and to perform basically to do your testing. So one example is say, learn to recognize different breeds of dogs. So the first task is to learn to recognize different breeds of dogs. The second task is to learn to recognize different type of animals. And the third task could be learning to recognize different type of fish. So you can see now if I, after I've done this learning and I present you an image, for example, it's a dog. And then, how do I classify it, right? It could be a particular species of dog, or just basically it's a kind of animal. So in this case, the user has to tell you which task this particular image comes from, and then you can use the model for that particular task to basically to do the prediction. So for example, I say I give you a image of dog and say, oh, this is task number 1. Then you basically predict particular breeds of dog. And if I say this is an animal, the second task, and then you just tell me it's the dog. That's good enough. Okay. So with this type ID, then we essentially say we are doing this function x cross t and basically map to y. So the t is the task ID. So every task has ID and that will be used. So this is a very simple setting, and this problem is pretty much solved in the sense there's no catastrophic forgetting, and also lots of knowledge transfer, which can be achieved. However, this second setting, which is incredibly difficult, is called a class incremental learning, and which produces a single model from all tasks. And then at the classification during testing, we have no idea of the task ID. Okay, for example, we say the task 1 is to learn to recognize pig and the cat, and task 2 learn to recognize sheep, task 3 chicken and dog, and task 4 horse and cow. So at test time, I just give you an image and you tell me what animal it is. Okay, so in this case, we don't have task ID, and you can see the function, the classification function is x mapped to y. So we don't have the t anymore. So in this case, it's extremely difficult. So the reason why it's difficult because when you learn the new thing, you have to incorporate the new sort of object sort of within the stuff you've learned in the past. So you cannot separate them. So in the previous setting, you can have separate models. But in this case, you cannot have separate models. You can only have a single model. And that's basically causes us lots of forgetting, because when you learn the sheep and you don't have the data for pig and a cat anymore, and then when you modify the network, and then you're going to cause a lot of forgetting, and this is challenging. So another problem with this, not just the forgetting, but the additional challenge is inter-task class separation. What does that mean is so after you have learned the pig and the cat, now you have to learn the sheep. However, you don't see the data of pig and the cat when you learn the task number 2. So in this case, I mean, how do you sort of find the discriminative features to be able to distinguish a sheep and a pig and a cat? So because you don't see those two animals anymore. And so there's no way you can do it to solve this problem, okay? And so we have to figure out a way, at least on surface, it's very difficult to solve this problem. But of course, we need to solve this problem. And this is called the inter-task class separation. And so there's 2 issues. One is, of course, is forgetting, because when you update the network, and then the parameters got modified, and then previously the stuff you learned in the past got sort of corrupted, and then the performance of the previous task will not be as good when it was learned and before. So the second issue is this inter-task class separation, and this is extremely challenging, and we have to somehow figure out a way to deal with this problem. So what is the way to deal with this problem? And then let's talk about something theoretical. And of course, I'm not going to talk about the theorems or all those things, but I'll just tell you the theoretical result. What is the result? Okay. The CLL problem, which is basic class incremental learning problem, can be decomposed into 2 subproblems. One is within task prediction. So when we're predicting within the task, so assume we know the task. Obviously, we don't know. But of course, the second, assume you know the task, then you have to predict the task. Then the second sort of subproblem is called task ID prediction. So if you can predict the task ID, then of course, within task prediction can be performed. Okay. In this case, we're talking about probabilities. We're not saying you must predict a specific task. We just the task ID prediction probability. So that's called a TP, and the first one is called a WP. So you can see this probabilistic formula. It says the X belongs to the big X. The K is the task, and the J is the particular class in the task. So the X belongs to a particular task of a particular class of a particular task. Is the probability is the multiplication of these 2 probabilities. And so given a task, so this is the first part. Let me see whether I can use a pen or not. No, sorry. The laser. Okay. So given a particular task, okay, given a particular task, and what is the probability of X belongs to a particular class J? Okay, the K is task, and the J is class within the task K. Okay? So this is what is called a WP, and the within task prediction, because we have the condition here. The second part is the X belongs to a particular task, and then this is the task ID prediction. So essentially this TIL can be written this way, probabilistically. So you can see, obviously we have a theoretical result say a good WP and good TP are necessary and sufficient for good CIL. So these 2 guys, so the WP and the TP must both be good in order to achieve CIL. Okay, but that's not enough. And how do we achieve TP? So this is a very difficult problem. And then we discovered, and you have to do OOD, sort of out of distribution detection. So which basically means when you build each task model, and that task model must achieve very good out of distribution detection capability. Okay, so what is interesting about this is previously the people study continual learning, and they just study continual learning, and the people study out of distributed detection, they study out of distributed detection. And now we're saying these 2 guys are actually connected, and they are basically similar problem, the same problem actually. the same problem. If you can do out of distribution detection very well, then you can also deal with sort of class incremental learning as well. So what is the intuition? The intuition actually has previously has a slide, but I removed that slides. And so the intuition here is you can see we have this problem of inter-task class separation, which basically means when I learn the task number 2, sheep, I have no idea about pig and cat, okay? And because I don't have the data of those things anymore. However, if I learn the sheep as the out of distribution model, then we have no problem. Basically says anything which is not a sheep, I will reject it for task number 2. Okay, and also for each task, I'm basically building an out of distribution model rather than a traditional classification model. So if we can do that, and this problem sort of can be solved in terms of theoretically, of course, in practically, we're still not able to achieve perfect sort of accuracy compared to you learn everything together. Okay, learn together. So here is sort of some experiments. You can see we have this experiment in the green box and shaded in green, and you can see the result improve dramatically compared to baselines, which is lots of baselines. The many techniques, and over this 5-6 years, and lots of techniques has been proposed, and lots of systems being sort of implemented, and we're still sort of pretty far in terms of the performance of continual learning compared to learn everything together in one go. And sometimes we call that pulling all the data together. Sometimes we basically call them sort of aggregating all the data together. So that's the upper bound. So we're still quite a distance from upper bound. Okay, quite the upper bound. However, recently, and we use the pre-trained models, and we can almost achieve the upper bound. So you can see the upper bound is there, is this line called the CL, non-CL, so the non sort of continual learning. So in this case, we pull all the tasks, all the data, all the classes together and learn a single model in the traditional supervised learning. And so this the pink part and also this TPL, this is the sort of we're doing sort of class incremental learning, but we have a pre-trained model in this case. And even the non-CL has a pre-trained model as well. So if you see the last column, you'll see the average result for each line, for each of this row. And you can see the last was last is basically we say we evaluate this after we learn all the tasks, and then what is the accuracy after we learn everything. Okay, and the AIA means it's an average incremental accuracy. It basically means when I learn the task, I do some testing, learn the second task, and do some testing, and the third task, we'll do some testing, and then we average the accuracy. So you can see the accuracy gets quite close. And so if you look at the line with the TPL, and especially for AIA, and it's getting quite close to the ideal situation. So basically the upper bound. Even when we look at the pink lines, there's 2 pink lines, and the continual learning can achieve 89.42, and the upper bound is 90.70, but 70. So you can see it gets quite close. So which means this theoretical results is quite useful in solving this particular problem. So now let's go to the open world. Okay, open world, which essentially means we have unseen or novel or unexpected object when we are basically doing application in the real world. For example, you have self-driving car, and then you have learned to recognize pedestrians, and recognize trucks and cars, and buildings or whatever. But now in the middle of the road, there's a little dog. For example, you have never sort of learned to recognize dog on the road, okay, on the road. And then you have to detect this is novel, this is a new object. And that's essentially the out of distribution detection, which is the OOD detection. Okay, so you need to detect this thing, and then you need to incrementally learn to recognize this object. So next time when you encounter the same kind of object, you will not have any problem anymore. Okay, so the issue is here is there are 2. So first thing you have to detect. The second thing you have to learn. So in order to learn, you have to have labeled data. Okay, so in this case, we want to get the system to be able to do all the things autonomously by itself. Okay, so in terms of theoretical result in learning, and you can see the previous theory can be applied here, because you see the detection of out of distribution detection, which is already covered in the previous the theory. And the incremental learning is also completely covered in the theory. So that you can see the theory says WP and OOD detection are necessary as sufficient conditions for CIL, okay, for the CIL. And then the OOD detection usually does both OOD detection and the in-distribution classification. So in-distribution detection is essentially WP. Okay. Then the OOD detection essentially is trying to achieve the task ID prediction. So it's basically the TP, okay, task ID prediction. So essentially that algorithm, the theory and the covers not just the CIL, but also open world continual learning. Okay. However, and the open world has additional task. So the first task, of course, is you detect detect the new object, and the second thing is you have to acquire some ground truth training data. How do you do that? And the third one is you have to adapt. For example, you're driving a self-driving car, and then this car hits something, sort of see something in front which is never seen it before. Then you have to react. You cannot just say, okay, I'll keep going, right? You either have to stop, you have to slow down, you go around of this object. So that's part is called adaptation. Okay. And I work on this sort of self-driven car for a year, and I was consulting for the company. And I had this personal experience was once we took a car for a test drive outside the company, and the road was pretty much empty, and there was no other cars because we're not that confident. We can sort of the car was so smart to be able to handle the heavy traffic. So when we get to T junction, and this car suddenly stopped, refused to move. I mean, we look around, we look at the front and the back and the forth, back and the left and the right, there was nothing on the road. Okay. Then this car doesn't want to go. And then the human driver to take over and drove to the lab. And then we have to do some debugging and see what's happening. And then we discovered one of the sensor detect a pebble, a very small pebble. For the human eyes, you don't really notice that. But this this sensor was very sensitive and then detect the pebble. Okay? And if in this case, and we have a dialogue system, for example, and the car can tell us, say, oh, I detect an object in front, and what should I do? And so as a human or as an engineer, we are sitting inside the car, we can just tell the car it's safe, just go ahead. So this essentially gives the system a supervised information. And the first thing is to recognize, I can even tell you, oh, that's a little pebble, you don't have to worry about it. So the system can basically detect this and recognizing as a pebble, as a class, and then also use the trace on the images or this the point clouds, and to learn to recognize this small object. And at the same time, you can also say, this is safe, I can just go drive ahead. So next time when I hit this thing, I recognize it's a little pebble, and also I know there's no problem, I can just go drive, and that will not cause any issue. Okay, so you can see this is kind of thing which we call the learning on the fly, and for people we say learning on the job. You can learn on the job. And for the chatbot, it's the same thing. Okay, chatbots, and we have the same kind of issue. And when you talk to a specific chatbots, and many times you get very frustrated, and the guy does not understand what you're talking about, and sometimes you just give you wrong sort of responses. So how can we make chatbot to learn knowledge? Means to learn things the chatbot does not know before, the type of knowledge never know before. For example, the chatbot never know sort of Obama was born in Hawaii, but through conversation with users, and they learn this piece of knowledge. So this is one thing. But another thing is to learn to recognize, to learn to understand language in expressions during chatting. For example, I say, and switch off the lights in the kitchen, but what happens if the chatbot did not understand that? Can the chatbot have a dialogue with me and and I can explain, and sort of the dialogue, the chatbot can learn and say, and switch off the lights and turn on the light, the turn off the lights are the same thing, and then the system will not have problem in the future. Okay, and we should get the system to do this kind of thing because we as humans do this all the time in our daily conversations. And if we say the chatbots is solely rely on the offline training initiated by the engineers, all this thing, and they is never going to learn, they're not going to be very smart. And recently we just published this book, and which is called Lifelong and Continual Learning Dialogue Systems. And my students and I wrote this book. It was published in January, the last month, basically. So what does that mean? That essentially means there's three orange lines. So we have this continual learning, and then we have during the application, and the system must detect new tasks, which is the orange line on the top, at the top. Okay, and when you see something unexpected, which basically means you have a new task to learn. And also through interaction, the system should try to get ground truth training data for that particular object, for example, and then learn to recognize that particular object. Okay, there might be some other information can be learned as well, but this, of course, is a fairly simple diagram, and we have a very complicated diagram which involves a lot of stuff, and I don't really have time to go into that. I'll just give you an example to finish up my my presentation. So let's say we have a greeting bot in the hotel, and let's say this bot is roaming around in the hotel and basically have a small talk with the hotel guests. And let's say when the bot sees an existing guest says, "Hello, John, how are you today?" So this basically just start with a simple conversation. And what happens if you see a guest which is new? And so this bot must recognize this person is new, and then this is also, of course, create a new task to be learned to learn to recognize this person. Okay, and this is out of distribution detection. Then the bot will say something like, "Welcome to our hotel, and what's your name, sir?" And of course, you may ask me why the bot say something like this. So this is basically the adaptation strategy, and which I don't really have time to talk about it. Okay, so the bot says, "Welcome to our hotel. What's your name, sir?" So the guest says, "David," and then you can see the bot gets the class label, which is called David, and then and presumably the bot has this cameras, right? You can take some pictures, some more pictures, probably go left and right a little bit to see the full image of this person and to learn to recognize this person. And then you got the training data, right? This is essentially the ground truth training data. And then we incrementally learn to recognize this person called David. And then next time when the bot sees the David, and then just say, "Hello, how are you today?" So becomes a person which is known. So you can see this process is completed autonomous, and there's no engineers or the software engineers or whatever those IT people involved. So the system can sort of do this and complete it autonomously. So this is our goal, and we try to achieve this. And I think to a large extent is sort of, especially in the simplest kind of situation, some scenario, this is probably achievable. Okay, this is probably achievable. So let me just close my presentation by saying, and CIL is a class incremental, is learnable. Of course, in this case, we have proofs, we have theorems, which published in the XML this last year, and also then we say the good OD detection for each task is necessary and a sufficient condition for CIL. Okay, and again, we say we unifies this and together with open world learning, and continue learning in the open world is basically the future for AI agents. And if you want the agents to basically to face the real world, to be able to handle things by itself, you need to be self-initiated and self-motivated, and in order to achieve this autonomy. And again, which is the same thing as I said about AGI. We're learning on AGI. We believe so learning AGI should be in the same fashion as well. And so we propose this thing called a solar self-initiated open world continual learning and adaptation. This was published last year in the AI magazine. This is essentially the position paper, just basically saying, we need to go this way. Okay. And so let me thank everybody. And if you have any questions, and I'll be happy to answer.
Thank you, Professor Bing. It was really a great, wonderful session, and I'm really grateful that middle of the night, it's around 11:30 in Chicago, probably. So in the middle of the night, you are giving this session, which is on a very, very relevant topic. But I sometimes, really wonder that along with the human intelligence, if we have to work with the artificial intelligence, it's a whole world of continual learning that we have to, work on. uh, about the message that you gave about the task that the AI has to do. There are a lot of challenges in that we can just anticipate. I mean, we use the chatbot sometimes, say Alexa and all. You try to give the different words to them. Sometimes you get a different answers, but then again they keep on learning. But similarly, my question was that we are working in the field of AI, but what is the thing that we can do to check for the trustworthiness of the AI, of their learning as well? Because it's a continual learning, and the learning may vary from a person to person. Like you gave an example of a self-driving, vehicle. So there was a small pebble that, vehicle stopped. It could have asked the human being, what is this small pebble, and we could have said, okay, go ahead. So the perception of a particular person may also vary. I mean, the user will vary. For me, the maybe pebble is bit large. For an elderly person, the pebble may be very very big. For a small kid, it may be a different. But for somebody else, it would be a different. So how we can take care of a individual's perception in giving the AI a particular way to learn. So that is important. I mean, we cannot have a uniform model in that case, but yes, it will depend upon the individual person who is using the AI for the benefit. So
Yes, absolutely. And for example, the self-driving car, basically, and that's your car, right? You teach the system, in this case, should I stop or should I slow down? Should I go stop basically to pick up the little pebble and throw it away, and then we drive. So I mean, you can teach the system whatever way you want to teach. And so I mean, the other people may feel this is safe, and you feel, I mean, this is not so safe. I think that's fine. And another aspect, of course, sometimes people always ask is, how can you trust the humans to teach the AI systems and without supervision, without somebody say, oh no, you are teaching this right way or wrong way. Okay. And we try to deal with that problem in the dialogue system. Just so in this book, we talk about this issue. And so, for example, I say Obama was born in Chicago. Then this is actually a wrong piece of information. But what we can do is, if I was talking about dialogue system, normally the dialogue system has a lot of users. So when we learn something from a particular user, we may not immediately use that piece of information. And we may just say, okay, after a while, I ask somebody else, oh, and by the way, do you know where was Obama born? Right? Or do you say, oh, was Obama born in Chicago? Then I can ask a bunch of people and as a system. Okay, then if many people say, the Obama was born in Chicago, then I can take that piece of information and I can use it in the future. But if I get some sort of conflict sort of information, and maybe so I will probably will not use that piece of information or piece of knowledge. So this kind of problem, and I don't think people have started to deal with this problem, but I think it's possibly, I think it's not something unsolvable. I think it's solvable if we just be careful and design sort of a mechanism to deal with this kind of problem.
Yeah, thank you, Professor Ling. I mean, great input we had into this continual learning in the field of AI and machine learning. That's very very vast. And again, the challenging part is to make a standard model by having a different people's perception on this technology and all. This is again a challenge.
Yeah.
But yes, it's a
Yes.
plethora of opportunities for the researchers in the field of machine learning. So thank you very much. We'll connect, after this conference as well to have more information, more knowledge from you in this field. And thank you for sparing your time in the middle of night. I'm really sorry you had to be awake, at this time for delivering this session. Thank you very much. Thank you.
Thank you for the invitation, and it's a pleasure. It's not too late, actually. 11:30 is not too late. All right. Thank